How do we determine its performance compared to, say, the shared memory paradigm?
So we are not getting into theoretical analysis, right? So you've got to run this and figure it out. But these algorithms are known to do very well in practice, right? So what is the work? The work is basically determined. The critical part is the number of neighbors that you're processing, right?
Yeah.
So it really boils down to this part.
Yeah.
Right? That how much processing do you have to do? Again, there are multiple things. I shouldn't just say that this is the only part. This is kind of like, let's say, an estimate of the kind of work you have to do. Because where does time go? Time doesn't really go here. The place where the time actually goes is this all-to-all V is going to be very costly.
Yeah.
Okay, that's actually where the time is going to go. Again, depends on the graph. This is bandwidth bound, right? The amount of communication you're doing is going to determine your performance. The data that you send from one node to another node, that's very costly in comparison to local memory operations that you're doing. So this frontier, adding it to buffer, these are not going to be very, I would not say that they're negligible. No, definitely not. But they're probably the second thing you should look at, right? Not the first thing. The first thing you should look at is reducing this all-to-all communication. Okay. How can you reduce that? And after that, of course, you have to look at this processing also. So by the way, I mean, one thing is that, the size of the all-to-all V is going to be proportional to this, what you're processing over here, right? The number of neighbors you're processing, because every neighbor you're adding to some buffer or the other, right? Which is going to be sent, right? So these two things are proportional, just that, the first part is just doing some memory operations, doing some lookups here and there, right? Or creating some buffer. The second part is actual communication. Again, you can't blindly say that, the first part will be a problem or the second part will be a problem. It really depends on the system that you're working on. If you look at traditional cloud-based clusters or something, right, the communication is going to kill you. You don't even have to worry about the first part. If you look at some of the very serious supercomputers of late, right, if you go to the top 500 supercomputing list, or there's a Graph 500 competition that's held every year, right? The Graph 500 competition, which basically optimizes all these algorithms on supercomputers. So on these supercomputers, you have very, very specialized and very efficient communication layers and very optimized interconnects. And you will realize that I wouldn't say that, the computation becomes the bottleneck. No, but the bottleneck is still all to all, more or less, but it's comparable to the other computations that you're doing. Right. So if you really want speed ups, you cannot just focus on all to all and be done with it. You have to look at the other computations. One very simple example I'll give you, right, is that I sent this vertex. So I have a vertex ID, right? And I have an owner for every vertex. So what have I added over here? What did I add to this buffer? I added this vertex. What does it mean? I added a vertex ID. So when I add, I say buffer w dot add vertex. So what is this? What am I actually adding? I am actually adding the vertex ID. This is some global vertex ID, right? Some global vertex ID that I'm adding. When I receive this on the receive side, now think of it on the receive side. When I receive this buffer and I have to go and modify this data structure, what do I have to do? I figure out where this vertex ID is in my memory, and I have to go and modify its level and so on, right? How do I do that? How do I go from vertex ID to memory location? Maybe I maintain a hash table, or
if the
what else can I
division
do?
was contiguous, you could maintain it as a contiguous memory location.
You could maintain it as a contiguous memory location.
As an array.
Yeah, that's one thing you can do. Then you have to know which global ID, global vertex ID your list starts from, your vertices starts from, right? So you have a global list of vertices, right? You have to know what is the starting point of that vertex ID. So you just subtract that, and then you can directly access into this array, right? So this array starts from your first, my vertex ID, my first vertex ID, maybe, my first vertex, and then +1, +2, and so on, right? So given this vertex ID, you just subtract my first vertex ID from that, right? And then you can do a direct access into this array. Okay. So this becomes a problem. This is okay as long as your vertex IDs are contiguous, right? So we spoke about different partitioning schemes, right? Or randomizing the vertex IDs or different partitioning schemes. So as long as you don't employ those, it's fine. If you employ any of those, then either you have to renumber all your vertex IDs or you have to do some other smart thing. Okay. Essentially, what we are saying is that in order to look up what node this vertex ID corresponds to, you cannot afford to do some search into some data structure, right? That is going to be very expensive. Okay. So it's not that, just take care of all to all, reduce that size, and that's about it. You have to be careful about the other code that you write as well.
So is there an implication on the complexity of owner as well? Because how will we maintain which processor this vertex belongs to if it is randomized, for example? So will we maintain a global data structure for that?
So that's a good question, and that's a challenge. So again, probably renumbering the vertex IDs may be the best way to go, right? So that the vertex IDs on each node are contiguous. Then you can simply divide by the number of processes to figure out that who's the owner. So there are n by p vertices on each processor, right? So if you have a vertex ID, you do a division by n by p. That will give you the floor ceiling. You'll have to take care of those things, but this will give you the processor number, right? And if you take the remainder with n by p, that will give you the offset within that processor. Yeah.
Yeah.
Offset within the processor. Okay.